Electronic configuration of atoms. We know that atomic orbitals are the substationary states, or the regions in space where the electrons revolve around the nucleus in an atom. The electronic configuration of atoms is a representation of the occupation of electrons in the orbitals. In other words, the electronic configuration of an atom specifies the order in which electrons fill up the orbitals in the periodic table. The order in which these electrons are filled into the atomic orbitals are controlled by three crucial guidelines or principles, which include the Aufbau or building up principle, Hund's rule, and Pauli's exclusion principle. Let's start with understanding the Aufbau principle. According to this principle, an electron always occupies the lowest energy orbital first before filling the higher level. For example, an electron always occupies 2s, the lower energy orbital, first, instead of the higher 3s orbital. The Aufbau, or building up principle, can be explained with the example of the hydrogen atom. Hydrogen has one electron. This electron enters the 1s orbital, which has the lowest energy. In other words, the building up principle states that the incoming electrons go to an orbital which has the least n plus L value. However, the orbital having lower n value will be occupied first, in case any two orbitals have the same n plus L value. Consider the example of silicon, whose atomic number is 14. 12 electrons can be accommodated in 1s, 2s, 2p, and 3s orbitals. Now, the last two electrons can enter into the 3p or 4s orbital. The n plus L values of these orbitals are the same. That is to say, 3p orbital has n plus L value of 3 plus 1 is equal to 4, and 4s has an n plus L value of 4 plus 0 is equal to 4. This means that both the orbitals have the same n plus L value, but the 3p orbital has an n value that is 3, which is less than the n value of 4s, which is 4. Therefore, the 13th and 14th electrons occupy the 3p orbital first. This means that the electronic configuration of silicon is Ne 3s2 3p2. The superscript represents the number of electrons present in the corresponding orbital. The second important rule to determine the electronic configuration of an atom is Hund's rule. It says that electron pairing happens only after all the available degenerate orbitals are occupied by one electron each. Let's use an example to understand Hund's rule. Consider the element oxygen with Z equal to 8. It has 8 electrons. The first electron goes into the 1s orbital of the K shell. The second electron will be paired up with the first electron in the same 1s orbital. Similarly, the third and fourth electrons will occupy the 2s orbital of the L shell. The fifth electron goes into one of the three 2p orbitals of the L shell. Let that one be 2px. Since the 3p orbitals, 2px, 2py, and 2pz, are degenerate, the sixth electron goes into 2py or 2pz, but not 2px. Let's say it goes into 2py. Since 2pz is a degenerate orbital, the seventh electron goes into 2pz instead of pairing up with the electron 2px or 2py. Now, since all three suborbitals have one electron each, the eighth electron can pair with any of the three electrons in 2px, 2py, and 2pz. So, the electronic configuration of oxygen can be written as 1s1, 2s2, 2px2, 2py1, 2pz1. The arrows indicate the electrons with a spin plus 1/2 and minus 1/2. Let's consider the nitrogen atom. It has 7 electrons. The first 6 electrons have the same arrangement as that of carbon, which is 1s1, 2s2, 2px1, 2py1. The 7th electron will enter only in 2pz, but cannot enter into 2px or 2py. This configuration is 1s1, 2s2, 2px1, 2py1, 2pz1. The third important rule for electronic configuration, that is, Pauli's exclusion principle, states that no two electrons will have the four quantum numbers the same. This means that two electrons can never have identical values of n, l, m, and s values. Because of this rule, a single orbital can have only two electrons.